So today I'm going to presenting my work that try to present the network systems perspective on how to utilize multiple channels availability in the cellular networks in order to improve application performance. This work is a joint work with multiple collaborators from different institutions. So as we know that low latency is pretty critical for lots of applications. For example, web browsing. For web browsing, an additional 100 milliseconds of latency can result in as much as 1% of revenue loss, according to Amazon. And for emerging applications, such as virtual reality, it requires less than 20 milliseconds latency to avoid any simulator sickness. And for cloud gaming, low latency is definitely critical to reduce the input lags. However, the current mobile broadband, such as 5G, has not yet delivered the satisfied latency. For example, in the current measurement conducted on the commercial 5G system that do the comparison with the 4G, they found that 5G does not improve latency too much compared to the 4G. Instead, these mobile broadband focus more on delivering huge bandwidth. For example, there are 5 times improvement in terms of the bandwidth for sub-6 gigahertz 5G and 10 times improvement on the millimeter wave 5G. However, the typical mobile applications such as web page load time only improve 5% on average, even though 5G bandwidth is 5 times larger. It is actually, we all know that it is fundamentally challenging to deliver a consistent low latency and high bandwidth because there is a trade-off between both of them. So does it mean that 5G don't give you a low latency performance? Well, actually 5G gives you a low latency performance, but it does it by providing a separate low latency service, or I call it as a channel in this work, in this presentations, which is called as the ultra reliable and low latency communication. This channel targets very low latency, such as 1 millisecond RTP-air latencies, but comes with a very small throughput, such as user throughput of 4 megabits per second, that come from that have a small throughput because it needs to maintain the consistencies of the low latencies that is provided by the URLLC. Because of its low throughput, it is planned to be used only for a very specialized latency-sensitive applications such as self-driving cars, factory automation, and remote surgery. And then we are coming with this kind of question: can we actually use this LLC to improve general applications such as web browsing performance? We know that we cannot rely on the URLC only because it has a very small throughput, like 4 megabits per second is not enough for general applications such as web browsing. And our answer is yes, if you use the URLC as a secondary channel. So the main question that we seek to answer in this presentations is, can we use high bandwidth channel and low latency channel in parallel to improve general mobile application? The high bandwidth channel will have a high bandwidth, high latency, and low latency channel comes with the low bandwidth and low latency. Our goal is clear. We want to get the best of both worlds, the high bandwidth properties and the low latency properties of both channels. And in these presentations, we're going to answer this question for the case of web browsing. When it comes to using multiple paths or multiple interfaces, multiple like channels, you might think about the multipath TCP, which is a transport layer protocol that allows you to use multiple paths. However, MPTCP assumes that each path has a significant bandwidth. For example, they use MPTCP a lot for the cellular and Wi-Fi case. And we know that in our case, the low latency bandwidth is very low compared to the high band HBC. And there are also related work that try to leverage multiple interfaces that are available on the mobile device, such as from the intentional networking and socket intent. These work are more like a complementary to ours because we are focusing more on how to split the traffic to both channels. I'm gonna deliver these presentations in this outline. First, I'm gonna talk about the background on 5G channels and then the background on the web browsing traffic. And then second, I'm gonna talk about how to split traffic on both channels. And then I'm going to follow up with some evaluations, and then I'm going to present some interesting discussion at the end. So 5G is different compared to the 4G because it provides you with multiple services. 4G only have one service and that's all. And 5G give you three services. The first one is the enhanced mobile broadband, or EMBB, which offers you a very high bandwidth, and it is intended to replace the 4G mobile broadband. So most of your applications on your cell phone will use this EMBB. And then you have the URLLC that allows a consistent low latency in the wireless link. Um, However, it comes with a very low bandwidth, so you cannot use it for like bandwidth intensive applications. And it is only intended for specialized latency sensitive applications. There are third service, which is focusing more on the massive connectivity, but because it is not that relevant to our talk, I'm just gonna dismiss it. So what makes the web browsing interesting in our scenario? Because it is dominated by short and bursty flows in which latency matters more than bandwidth. However, it still requires a considerable amount of bandwidth. For example, a study conducted by Sundarasan et al. Shows that you need at least 16 megabits of bandwidth before the latency become a main bottleneck for the web page load time. So we're gonna answer the questions of how to split the traffic to both channels. The problem formulations is assume that we have two channels, the high bandwidth and high latency, low bandwidth, low latency channel. And the idea is we want to offload only a small portions of the traffic to the LLC because LLC have a very low bandwidth. We don't want to overload it with data that will build up queues and congest and finally inflate its latency. However, that small portion should yield the most benefit for the application performance. And we investigate two levels of granularity in terms of the splitting. The first one is the application level, or for the case of the web browsing is in the web object, where a client can request an object doing an HTTP request and response through one of this channel. And then we also try to explore a finer grained approach by delivering in the packet level, splitting the packet level to both channels. First, for the object level splitting, because web pages consist of multiple objects, and each objects actually have different sizes and priorities. And we explore two heuristics based on the size and priority hint. There are lots of details here, but I won't discuss too much about this object level splitting because in conclusion, it is actually not a good match for LLC that has a small bandwidth because this approach is too coarse grained, and we actually need a finer grained approach for the LLC that has a very low bandwidth, such as URLLC. So in order to explain more about how the network splitting works, these are the HP traffic in terms of the networking level, like traffic. So the client will first exchange packets, which is the TCP handshakes to the server. You have a SYN, SYN-ACK, and ACK. And then the client will also exchange another packets to build up a TLS handshake. Then the client can start sending a request to the server. The server then responds with the data, which is in terms of the HTTP response. But this particular response is pretty big, so it needs two RT keys in order to fully deliver the data. And then after it received the data, then the client decided to ask for another request. And the server gives you a response of the objects, but this response is pretty small, so it can fit in just one single packet. And then finally, the client close connection to the server. The main questions is, how do we map network packets to LLC and LBC? Remember that the guideline is we need to offload only small portions of the traffic to the LLC, but that traffic should yield the most benefit. For this case, is the flow completion time. So we devised three kind of packet level splitting heuristics. The first is based on the observation that uplink traffic, which is the client to server traffic, is small because generally client requests are small. So we devise a scheme called as packet uplink, where it will offload uplink traffic to the LLC and downlink traffic to the HBC. This approach will definitely reduce the flow RTT that will further improve the flow completion time. However, it might not perform well when a client pushes large data, for example, via HTTP post. And then the second heuristic takes a look at different types of the packets. You have a control packets that are intended for controlling the operations of the connection, such as the SYN and SYN-ACK in this case. And then data packets, which is basically packet that contains the data. And we observe that control packets are small because it does not contain any data. So how about if we offload control packet to the LLC and data packet to the HBC? By doing this way, we will reduce connection time here, and then we will also reduce the flow round trip time to some extent, for example, in this kind of transfer. However, we think that we can do better than this because we want to offload more aggressively. And we noticed that there are some data transfers that are small that we can actually accelerate. For example, we can accelerate the first request here or the second response here. But we definitely need to avoid offloading any packets that are belong to the larger transfer. For example, in this response, we definitely want to avoid delivering any packets in this response because it can quickly consume the bandwidth of the LLC, and accelerating just one of the packet will not be any use. So we devised a scheme called as packet state, which is currently our best scheme for this particular thing, where we offload control packets and small data transfer to LLC, and we send large data transfer to HBC. By doing this, we will improve connection time and small data transfer, and also reduce flow RTT. So I'm gonna explain about the evaluations that we do. We're gonna answer multiple questions on these evaluations. The first is, how much can dose splitting improve the web page load time compared to when you only delivered it throughout the HBC, which is your typical mobile broadband? And then how our approach performs when compared to relevant work such as MPTCP or ASAP, and how much LLC bandwidth that we consume, which is important because LLC bandwidth is very restricted. We want to make sure that we only use little portions of the bandwidth. And then how the PLT improvement change when the network conditions change. We use the emulation for all of our experiments by emulating the 5G MBB and URLLC network characteristic. The 5G MBB will give you 30 milliseconds of RTT with 60 Mbps upload and 1,500 Mbps of download, while the URLLC give you a faster latencies, 5 milliseconds RTT, but only up 2 Mbps, 2 Mbps bandwidth. We use Mahi to record and replay web pages. And we also additionally emulate content delivery network caches. So there are some objects that can be served by the edge server, but some objects might need to be fetched from the origin server. So it will later increase the latency. These are the summary of our schemes that we evaluated. There are 3 objects level and 3 packet level splitting level. And then we also tested relevant approaches. So for these are the page load time improvement. The x-axis is the page load time improvement in terms of the percentage when you compare it with the baseline, or in this case is when you offload all of the traffic to the eMBB. The y-axis is the scheme that we used. And in this particular graph, I use the distribution kind of graph. So you can see the distributions of each pages of the pages improvement. Based on this setup, we see that the object level, which is based on the priority or based on the size, is actually too coarse grained for URLLC. And it does not give you a consistent improvement. For example, only 5% of the pages have 10% of better PLT. However, if we do it in a more finer grain, which is by using a packet level, it performed consistently well because at least no pages that are worse than the baseline. And the best is actually the packet state where where we gain 26% of better PLT by only offloading 12.6% bytes to the URLC. And MPTCP performed worse in this case, which is not surprising because it tends to load balance the traffic. And we know that we need to use the URLC bandwidth very carefully, and we cannot just randomly send packets to it. And what thing interesting here is the ASAP actually performs not that far away from the packet state. But we all additionally test another scenario where we try to do the interactive browser session, where a user visit landing page and click through internal 4 pages. And in this case, ASAP does not perform that well. Like the packet state can give you a consistent improvement across pages, while the ASAP only improves the landing page. I won't do lots of details about ASAP and like how this kind of thing happens. You can take a look at the papers, or you can ask me the questions like in the Q&A session. And we also evaluate how much traffic that we send to the URLC. And we found that packet state only puts little pressures on the URLC because we offload only 12.6 traffic to URLC and only consume less than 1 Mbps on average. The next thing that we tested is also interesting, where we try to vary the main channel, which is the eMBB latency. And then we found that improvement increases as the eMBB latency increases. So we bumped up the eMBB latency from 30 to 150, which can happen when you are under mobility, or when the queue when there are some sort of buffer bloat in the eMBB. And interestingly, the PLT on the packet state is pretty robust to the eMBB latency change. Why? Well, it is because we've already offloaded most of the latency sensitive traffic to the URLC. That's why it is pretty robust to the eMBB latency change. There are few discussions, which is also part of our future work. The first one is, how do we implement this packet steering? We present 2 alternatives. The first one is we might need to introduce a new MPTCP scheduler that do this kind of scheduling. Or the second one is to present a virtual interface that works transparently from the client and then server. And the client can steer packets via the custom bridging. The core network also needs to steer packets incoming from the internet because the steering comes from both ways. And then the matter of whether the operators will deploy this and allows the URLC to serve general traffic is in the hand of the operators. Right now, the URLC is not yet deployed in the real world, but we believe that if operators are gonna deploy this and allow the general traffic to be served by the URLC, it can bring a smoother experience to the major user, which is cell phone users. And it can also opens up so many applications that can use this URLC. And then we also argue that for the future wireless network design, we might better to rethink the trade-off between bandwidth, latency, and reliability by providing a service like URLC with a moderate bandwidth, like more than 4 Mbps to serve general traffic. But we can probably do it by sacrificing reliability, because this general application does not need a point like 99.999% that the URLC guarantee. So these are some several final thoughts. It is interesting to leverage the availability of the eMBB and URLC beyond the simple static assignment. And we show that if we carefully use both channels, it can outperform both if we only use eMBB and both if we use URLC only. And this one is another interesting point is if we use these channels in parallel, it offers you with an illusion of both having a high bandwidth and low latency channel in the single service. which is a good match for a high bandwidth, low latency application, such as the VR, AR, or cloud gaming, and that cannot be satisfied by the eMBB only. That's also, thank you.